So on our data booklet, the back page, you look at here, we have a voltage given with each half cell. These are all called half cell reactions, okay? And when you combine them, you get a cell. So how do you get the voltage of a cell? Is what we're going to do today. All right, so let's go back to the iron copper electrochemical cell, which we did the other day. We're doing this one. This one. All right. So this is what we originally did. The anode is iron. It's producing the electrons. You're getting iron electrode is dissolving, producing 2 electrons. Copper is picking up the electrons and it's increasing its mass. So what is the overall voltage of this? Well, the anode reaction was copper plus 2 electrons goes to copper solid. And the... Oh, I wrote that in the wrong spot, didn't I? That's the cathode reaction. Sorry. There you go. Cathode reaction is where reduction occurs. And then the anode reaction is the iron producing 2 electrons and dissolving into iron 2 in solution. What is the E naught of the copper reaction and of the iron? So go to your table. Copper 2 plus is right there. Copper 2 plus 2 electrons going to copper solid is 0.34 volts. And then the other one, iron 2 plus 2 electrons is right here at the bottom, is negative 0.45 volts. But it's not written that way, right? It's written as iron going the other way. So the E naught of the first reaction, as written, pulled off the table, you don't change anything, it's 0.34 volts. If you take E naught, like the half cell voltage for that reaction. They're chemists. And then the next one, iron, we flip the reaction. If you flip the reaction coming off the table, what do you think you do? You flip the sign of the voltage. So it's going to be negative of negative 0.45, which obviously becomes 0.45 volts. How are you going to figure out the overall voltage of the cell? You're just going to add them together. All right. The subtraction part is if you don't flip the sign. So I just say flip the sign and add them. It's a little easier. So the overall voltage, so the E of the cell is going to be 0.34 volts plus 0.45 gives you 0.79. So that cell should produce 0.79 volts. Okay. The only trick here is when you pull it off the table, if you're flipping it and turning it into an oxidation reaction, you must switch the sign. Okay? And this is the maximum voltage. This will probably not in reality be the actual voltage. All right? Because you'll see in a sec, it depends on concentration, and then there's a lot of other things. There can be resistance and things like that in the wires. Okay? That's the theoretical max voltage you will get out of the cell. Okay, so a pretty standard question you would see is we have an electrochemical cell. We're using nickel electrode immersed in nickel electrolyte and a zinc electrode with zinc electrolyte. Determine the standard cell potential. So again, we're going to look up zinc and nickel. Which one is going to be reduced? Which one's the stronger oxidizing agent? Go to your data booklet. I mean, this is the reaction we just wrote up on the board. There's zinc right there. There's nickel right there. Nickel wins. So nickel is the one that will be reduced. That we did not. Did we change it when we pulled it off the table? Did we rewrite the reaction or flip the reaction? No. So negative 0.26. So back here. That gives an E naught of negative 0.26 volts. We do flip the zinc so that it's zinc solid. And because we flipped it, we have to flip the sign. And off the data table, zinc is negative 0.76. So it's negative of negative 0.76, which is obviously 0.76 volts. Add those together and you're going to get 0.5 volts. That's the theoretical max amount you can get out of the cell. Okay? Are we good with that? That's all we're doing. It's basically, if you have to flip the reaction to turn it into an oxidation, you just flip the sign of the voltage. All right, going once, going twice. Well, they're all going to be, I think they're all the 2 sig figs. So that one should have been 0.50. So, all right, spontaneity. Okay, how do you know if a reaction is spontaneous? If it has a positive voltage. If the voltage is positive, it is a spontaneous reaction. If it's a negative voltage, it does not happen spontaneously. You can force it to happen, and we'll look at those types of cells. That's what we'll look at when we get back. Electrolytic cells, where you have to hook it up to a battery to drive the reaction. Okay. So if we look at this reaction, aluminum ions plus 3 silver, does it go to aluminum solid and 3 silver ions? So the aluminum is written as a reduction because it is gaining electrons, going from aluminum plus 3 to aluminum solid. So on the data package, aluminum, where is aluminum? There it is right there. Negative 1.66. We're taking the reaction as written, as a reduction. So we don't change the sign. So it's negative 1.66 volt. 66 volts. The silver, where is the silver? There it is, up here. All right. The silver, we have to flip, all right, because it's silver solid going to silver ions. So it was positive 0.8, is now going to flip to negative 0.8. Add those together, you get a massively negative 2.46 volts. So does this reaction happen spontaneously? There you go. So it is not spontaneous. What would be spontaneous? Yeah. The reverse reaction would be spontaneous. Okay, so if you react aluminum solid with silver ions, you'll get a spontaneous reaction going the other way that would produce a max voltage of 2.46. Noah.
Is it possible to
electrons, right? But that would be tricky because it leads us into this part. So if I take the silver half reaction, silver going to silver plus 1 and 1 electron, if I'm going to multiply through by 3, that does not change the voltage. It's not dependent on the half reactions. It's dependent on the concentrations. Okay? That's what we're going to talk about down here, okay, in a sec. So the number of electrons written in the half reaction does not determine if it's going to be a stronger voltage and things like that. It's dependent upon the concentrations are one thing. And I can show you this. There's an equation called the Nernst equation, and it has logs in it because we all love logs. All right. I'll show you that. I might show you today. We don't deal with that in this class. That's higher level chem. But then you get into altering the concentrations. If you noticed all the cells that I've shown you, let's show you this. All the cells that I've shown you are, I don't even know if I set them in here. These electrolytes are at the same concentration, which is usually 1 molar. Okay, but you can alter the concentrations of these, and then that will change how the cell is working. Okay, but we do not do that in this class. All right. Okay. So, standard hydrogen half cell. So if we look at our table, right in the center there, they designated that the 0 voltage half cell. That is completely random. They just decided that. Okay, they said this is going to be the 0, and then all of these things are just measurements of differences in reactions. Okay, they could have said that we want the tin 4 to be the 0, and then everything will be based off of that. Okay, it's just an arbitrary point. Okay, so we call all these things standard half cell potentials. All right, and we choose the H2 to be the 0 point, and everything's based off of that, positive and the negative below it. So the voltage will vary depending on not on the number of electrons, like we just talked about up here in the half reaction, but on things you can control. So the concentration of the electrolyte, the temperature of the system. When you're talking about gases, which we'll talk about as well later on, what's the pressure of the gas, things like that. So this all ties back to KEQ stuff that we did, all right? But when we say standard, we have certain things that we have to meet. So the standard temperature of the system is 25 degrees. Concentrations of all solutions are 1 molar. Make it nice and easy. And the pressure of all gases is 1 atmospheric pressure, or does anybody know what it is in kilopascals? 22. That's moles. That's the liters of 1 mole. Yep. 101.3. I don't know how you guys didn't know that. Come on. I'm joking. That's what 1 atmosphere is. All right. So that's what that little superscript is. I say E naught. It's actually means standard. Okay. All right. So that's under standard conditions. All right. And that's everything we're going to deal with is standard conditions. If you go on, you can do non-standard conditions. I have the Nernst equation. I'll pull up the Nernst. Oh, there it is. So this is not part of Chem 12, but just so you know, if you go on in chemistry, sorry, it's not. This is the Nernst equation. So notice E, so voltage of the cell, all right, is going to be the standard voltage, which meets all these conditions, and then we change things. R is the gas constant. It's 8.314, blah, 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 blah. If you go on in chemistry, you will see it all the time. T is temperature in Kelvin, okay? N is the number of moles. F is called the Faraday constant. And then everybody's favorite little bit, the natural log of the concentration of the reduction, so the cathode reaction, over the concentration of the oxidation reaction, which is the anode reaction, okay? We make these 1 and always the same, which gives the natural log of 1, which is 0, which wipes all that out. And so then we can say it's under standard conditions, E is equal to E naught of the cell. That's why we do that. So we just make the conditions all 1. All right, so all that disappears, so we don't have to worry about that. If you go on, then you get to play around with that and use calculus on it. Of chemistry? It's to be a 245 or 345. Remember when I talked about those classes that bring physics and chemistry and calculus all together in one happy vortex? Well, if it starts with a 2, it's second year. If it starts with a 3, third. If it starts with a 4, fourth year. Look at, we're learning fast. First year starts with 0. No, this is 0 right now. 0, 1, 2. Chem 12. Yeah, but those are still first year classes. It's just derivatives or part. It's most like partial derivatives because you'd be holding one thing constant, right? So that's Math 200. I just say Math 200. Sorry? Yeah. But UVic will call it Math 200. I just call it Math 200 because that's what I want. But yeah, Calc 3, I guess. Okay, so because we're dealing with concentrations can increase and decrease depending on what's happening at each half cell. All right. When they drop, all right, the cell voltage, like no battery goes forever. It's when you use up all the concentrations of things, the voltage drops to 0 and the battery no longer works. Okay. That's what happens when a battery dies. You've used up all the electrolytes or the everything for the oxidation reaction to happen is all gone. Like when we looked at the electrodes, when we had what was it? I can't remember. The lead electrode is being dissolved and forming lead 2 ions. When this is gone, the battery stops. Okay, when you use up all the reactants, essentially, just like every other chemical reaction. At a certain point, it's going to stop. All right. Now, reversible batteries, you can drive it back the other way, but what do you do for a reversible battery? You plug it into something, which is just electrons, which then just forces the reaction back the other way, which is what we would call an electrolytic cell, which we'll do in the very last week. You can drive reactions using electricity as well, depending on what you want to make. Okay. That's it for standard reduction potentials. Questions are there. I'll post the key in the classroom. I think we might stop here for your test on Tuesday. So everything up to this point. Okay. Tomorrow,